Hello and welcome back to the first course on quantum field theory. Now in this lecture we'll talk about the mathematical structure of special theory of relativity. Now in STR the three spatial coordinates are and the time define the four components of the position vector. So we can write it as the three spatial component. Okay, three spatial and one time component. They define what's called as the four vectors, which we denoted by x mu. Now, before we move further into this lecture, I already assume that you know special theory of relativity. So I won't be going into much detail. I'm just going to briefly touch upon the mathematical structure of STR. So yeah, that's what it is. So yeah, I want to be a bit careful about the notation here. So notation. So we will use the Greek indices. Greek indices includes such as mu, nu, lambda, and so on. They take the values from 0, 1, 2, and 3. We will mainly use the Greek indices, which take the value 0, 1, 2, and 3 for defining the components of four vectors, as opposed to the Latin indices. They include letters such as I, J, K, and so on. They take the values 1, 2, and 3. They do not take the values 0. I want to be very clear with this. And they are used to define the spatial coordinates. So these are the two notations that we will use throughout this lecture, throughout this course on the quantum field theory. So let's go ahead and we define what's called as the contravariant vector. So if you have studied the special theory of relativity, you might know that there exists something called as contravariant vector and covariant vector. So contra means up. So index that we use must be up, that is x mu. So the index that we use is up, and as per our notation, they take the values from 0, 1, 2, and 3. Now we can write this part more compactly by defining it as x to the power I. They define these spatial coordinates, they are Latin indices. So yeah, this is CT x vector, and we'll keep our equation number intact. So this is equation 1.29, where this factor C, you see the factor C, you might know this from STR, is put so that all the components have the same dimension, of length, So that is the reason the C is put. So the interesting thing is the distance L between any 2 points. Take any 2 points. Say this is as x, this is as y. The distance L between these 2 points in the space-time can be rewritten in terms of the Cartesian coordinates. So this is L square x naught minus y naught square in space-time. I want to be very clear when I say space-time. Space-time naught square minus summation, which includes I is equal to 1 to 3. Okay, the 3 should be here. Xi minus yi square. But this is not a very compact form. Now what we can do is we can write in a very compact form by defining something called as metric tensor. So what we can do is we can write the L square G mu nu x mu minus y mu x nu minus y nu. This is equation 1.30. Now you might ask a question, here we included the summation sign, why are we not doing the same here? This is because we use something called as the Einstein summation convention. Let me mention it explicitly. Einstein's summation convention. Now it's not that great big of a deal. It just says that the repeated indices are summed over. You don't need to put the summation sign explicitly. It just implies the summation is already been implied. You don't need to write it explicitly. It just saves you some part of the writing. That's why Einstein introduced it. When I say repeated indices, it means see the mu in the upstairs and the mu in the downstairs, they are contracted. They are repeated indices. They are summed over. New and new year. They are summed over. This is why we didn't introduce the summation convention. We didn't introduce the summation explicitly because it's already implied by the Einstein summation convention rule, if you want. So what? So yeah. So I didn't mention. So in this case, the value of G mu nu is diagonal 1 minus 1. Oh, minus 1 minus 1. So this is equation 1.31. So which means, what does it means? We can write it explicitly. G00 is plus 1, G11 is equal to G22 is equal to G33 is equal to minus 1. This part is this and this part is this. And G mu nu, where mu and nu are not equal, we get 0. So this is what it means explicitly. Now once we have what's called as the contravariant vector, we can define covariant vector. So co means low. So yeah, an interesting analogy if you want to remember what, like most people get confused like what's contra means low or up, co means low or up. Even I used to do it. So I used to get confused. So my professor just told me that co means low. So an interesting analogy to remember would be to use co means low. So this implies that when I talk about covariant vector, it means the indices should go down. So we can define covariant vector by using the metric G mu nu, X mu nu. We don't, so this is summed over. So we don't need to include the summation sign explicitly. What we can now do is we can explicitly write this down by 0 x0 plus g mu 1 x1 plus g mu 2 x2 plus g mu 3 x3. Further, we can go ahead and put g00 g00 x0 plus g11 x1 plus g22 x2 plus g33 x3. So this is nothing but what we have done earlier, which is ct comma x minus x vector. So this is equation 1.32. So yeah, what this means is it's a good thing that we can define the inverse metric, which is G mu. Okay, inverse metric, which is diagonally 1 minus 1 minus 1 minus 1. This is equation 1.33. Now you can see that G mu nu on the upstairs and the G mu nu downstairs are symmetric metric, symmetric metric tensor. They are symmetric tensor. So it doesn't matter if you write G mu nu on the upstairs or G mu nu downstairs, but it should be consistent with what you write next. So that's what matters. But they both are symmetric under the exchange of the upstairs or downstairs. So they are symmetric metric. We can go ahead and define the inverse metric. Yeah, we already defined it. So we demand that the inverse metric must satisfy G mu nu. No. Yeah, we'll take mu and we'll change the next index. G nu lambda, which is a new index. So mm, they both are summed over and we can write this. So this is basically just a rule. You can find in any standard STR book. If you had a very good STR course, that you might know this. Mu lambda. So we can go ahead. Oh, what just happened? Okay, just ignore this. That's a mistake. So this is 1.34. So where what does this means is this is nothing but the Kronecker delta. So you know this, that this is Kronecker delta, which is defined like if mu is equal to lambda, then it's 1. If mu is not equal to lambda, this is 0. This is simply equal to 0. So we can see that if we can write the component form of it, we can write it explicitly to see what this means is G mu 0 G0 lambda plus G mu 1 G1 lambda plus G mu 2 G2 lambda plus G mu 3 and G3 lambda. This is equal to 1. You can explicitly see this. Again, we don't need this. We'll be mostly using this type of equations. We'll make it more compact, because when you go on studying quantum field theory, you will realize that more compact it is, the better it is, because you have so much equations to write and suddenly you come up with a very a huge formula to write. Then this compact equation helps you down, it helps you narrow it down, and it helps you keep the indices aligned so that you don't make any mistake while writing the equations. So that's why we go for using the compact equation. Now another concept which is very much used in special theory of relativity is the concept of Lorentz transformation. Any discussion of STR is incomplete with the Lorentz transformation. So under the Lorentz transformation, the coordinate transforms in the following way. If I have x mu nu as the 4 vector, as the position 4 vector, I can transform it to some other coordinate system using this particular rule. This is equation 1.35. So I have a 4 vector in this particular coordinate system and I make a transformation in some x dash coordinate system. This would be my rule. Now this is again a metric. This is again a metric. It's we'll see. I think I have a problem on it, so you might get some handling on this, so that's fine. We have a problem on it, so we don't need to go for it. So what we are doing is, I want you to understand very clearly. So what we are doing is, we are demanding that this transformation are defined to be the one which leave x mu invariant. You understand what I'm saying? uh, if you don't, it's fine, because let me write it down more mathematically, so you might understand what I'm saying. Okay, my handwriting is getting bad and bad. I'm really sorry about this. So we have what? Okay, so we have x dash mu. So this is generally written as x dash mu, x dash mu. I just changed this indices by introducing this metric, and I've shifted it above. That's what we saw here, right? That's what we saw in this. That's what we saw here, right? We introduced this metric. We change the index from mu to mu, because here you have mu. So the right hand side should also have mu. That's why we contracted this. They are contracted. The free index, the left index is mu. Here also we have free index as mu, so that's balanced. So an important rule that I forgot to mention is, how did I forget to mention this? Okay, the important rule is, if you have a free index, like if you have mu on left hand side, you must have mu on the right hand side. The indices should balance. You're getting my point, right? Here mu and nu, they are contracted, but the free index mu is same as the free index that appear on the left hand side, so they must be balanced. So that's one of the rule that you need to follow, so that helps you keep your indices balanced. Basically like in physics, many of the physicists tell that this is called as indices gymnastics. They have a new term for it. So basically this is used in general relativity. uh, that's what my thesis is based on, so I know this. So what we can now do is, we can use this definition and we can rewrite it as mu. Which index should we take? We'll take rho, x rho sigma sigma. We merely introduce this definition. We merely introduce this definition here just by keeping the indices contracted. Okay, they are contracted. Now you see it's balanced. So this can be written as, this must okay, wait, yeah, just merely shift it. Now it looks like, so this must be equal to G you understand, right? This is, you can get this in any STR, a good STR book. So this is the, so what we have done is, we merely contracted this indices to get a new metric. If you use this metric here, it's balanced, it's contracted, there are no free indices here. This is contracted. Here on the left hand side, if you see, there is no free index. Mu and mu are contracted, that means there is no free index. So this must be, the case for the right hand side as well. So if we use this, so this must be equal to this, or else there will be, the free index will be left. There will be no free indices. So that's the point. That's the whole point. So what does it mean is, this legitimately satisfies the Lorentz transformation matrices. So we will call this as equation 1.36. 1.36, that's what we used, I think. Yeah, 1.36. and and for some reason, I don't know why, I mentioned this as 1.40 in my book, so we will keep it, or else I'll just keep hammering the equation number. So in order to avoid this, I'll call this as equation 1.40. So now, to get a better understanding of this, we can do two problems which I already have written down here. So the first problem is this exercise 1.5, using the definition of equation 1.32. What is 1.32? We can go and check what is 1.32. Okay, so this is the definition. Okay, I'll write it again. Yeah, maybe. Using the definition in equation 1.32, show that the Lorentz transformation rule for x mu lost is given by this. Okay, okay, we can show it. We know it's easy. It's easy. It's not that difficult. So, okay, fine. Oh no no. Okay, let me solve here maybe. Solution to exercise 1.5. Let's do it. So it said that using the definition 1.32. So just to remind you what 1.32 is, x mu is equal to ct dash. This is equation 1.32. Just a remembrance. We are show that the Lorentz transformation rule for x mu is given by x mu x dash mu x. So we will start with the definition. We can write x mu as g mu nu x nu, right? We know this from the definition. Okay, I'll just, yeah, we know this from the definition, and we can further write x mu as x dash mu is equal to g mu x dash nu, and this is g mu nu lambda mu nu sigma x sigma. You can take any indices. I'm just taking sigma because that's how the order goes. So I'm used to this order, so I'm using this. We can further write it as lambda x nu and g. I will be lowering this because you see we have a lower index here, so it's better to lower it down. We use theta x theta. So this by definition is theta mu. This is mu lambda theta mu x theta. So we will use something, since see, I know. Okay, the sum. Okay, wait. This summed indices, this theta is summed over, right, by Einstein summation convention. This is a free index. Okay, it's a free, no, sorry, it's called as, I'm sorry, I'm really sorry, it's called as dummy variable or dummy index. We can replace theta with nu. All right, we will have nu mu x nu. Is that right? Yeah, that's right. That's equation 1.41, and this is x mu. Is it x mu? Yeah, it's x dash mu, and we, now you see we have the Lorentz transformation rule for x mu. This is the Lorentz transformation rule for x mu. That's beautiful. We have done it, and we have done the problem 1.15. Nice. Oh, okay. This problem is lengthy. Okay, we'll do it. If a primed frame of reference moves with respect to an unprimed one with a uniform velocity v Okay, this is V, not V prime. Please be careful. This is V. Along the common x-axis, the Lorentz transformation equation between the between the coordinates in two frames are given by this equation, and this is equation 1.42, where gamma is 1 minus b square c square minus half. We know this. This is standard STR notation. Show that this transformation can be written in the form of 1.35. What is 1.35? 1.35, yeah, yeah. Which is the Lorentz transformation. Okay, okay, fair enough, yeah. Which is the Lorentz transformation rule. Yeah. Mm, yeah, fair enough. With this given condition. Okay. Let's just start with and we can proceed, I think. Yeah. We can do this. This is not a big deal. We can do this, yeah. This is solution of exercise 1.6. Right. So we'll start with the given condition as usual. X mu is x dash mu. So if a prime frame of reference moves with respect to an unprimed one, so we have to use this condition. We have no other choice. And this is given by equation 1.35, which is just the condition we derived. X mu, x mu, x mu. Alright. So we know that x mu is defined as Ct x vector. Uh, So what we can do is from this equation 1.42, which is this given condition, we can write them. We can write them as Ct dash is gamma times Ct minus gamma V by C x, and x dash will be uh, minus gamma V by C Ct plus gamma x. Uh, this is gamma, and y dash is just y, and z is just c dash is just c. There's no change in y and z dash. Now what we can do is we will write this in a matrices form, because that will give us more advantage, and since we already had a course on linear algebra, so it will be very handy for us as well. So y dash c dash, this matrix is going to be big gamma minus gamma b by c 0 0. This is minus gamma b by c gamma 0 0 0 0 0 1 0 0 0 1, and this is ct x y and z. All right, that's beautiful. So we know this x mu is x dash mu is equal to lambda mu nu x nu. So what we do is we will, I think, yeah, it's better to change the indices, because yeah, that will be confusing. We'll change the indices from mu to theta. That's better. Theta, theta mu x mu. Just change the indices. What I did is I just changed the mu to theta and the uh, mu to nu to mu. So why I did that, you will see. This is just to make sure I understand that I don't make any mistake. So this is equation 1.43. We know this condition. We are just using it. We are using the definition. Now what we can do is we can write this in a very expanded form. uh, yeah, we'll write this in expanded form maybe. Okay, so we know that this is just the diagonal. Okay, you remember this diagonal 1 minus 1 minus 1 minus 1. G mu theta was, yeah, G mu nu in that case was 1 minus 1 minus 1 minus 1 diagonal metric, and this metric we know in, this is the metric, this is that metric. So we'll just use this metric. This is 1 0 0 0. This is 0 minus 1 0 0. This is 0 again, 0 minus 1 0 0 0 0 minus 1. Okay, now this metric we just used above, minus gamma b by c 0 0 minus gamma b by c, gamma 0 0 0 0 1 0 0 0 0 1. We can multiply this metric, these two matrices, and we will get gamma 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 b by c 0 0 minus gamma b by c minus gamma 0 0 0 0 minus 1 0 0 0 0 minus 1. The metric, so this is the matrix that we get by multiplying this, and this is equation 1.44. So but we know that since gamma is given the value as minus b square by c square to the power minus half, so what we can do is, in the limit where v is much smaller than c, we can use the Taylor expansion. No, we can use the Taylor or binomial, anything. We'll just, anything, any expansion that we want. We can expand this. We can expand, and we will get 1 minus b square upon c square to the power half 1 plus b square by c 2c square plus 3b4 8c4 plus, what we do is we'll neglect this happily. We are going to neglect it happily. We will terminate until this. So in the limit, as I said, in the limit where b is much smaller than c, we can approximate 1 minus b square to the power half to be 1 plus b square upon 2c square. This is equation 1.45. Thus our metric, thus our matrix. I'm so used to the word metric, I'm not able to say the word matrix. I'm really sorry about that. So thus our metric 1.44 can be written using this equation 1.45, can be written as 1 plus v square upon 2 c square minus v by c 0 0 v by c 1 minus v square, minus, yeah, 0 0 0 0 0 minus 1 0 0 minus 1. This is equation 1.46. So this matrix 1.446, this particular matrix can be splitted into two different matrices. You can see how, right? You can see how. You see this, you see this, you see this, you see this. You see this too, second term, second term, second term. Here we don't have, so we can consider plus 0. So we can split it out into two different matrices. That's the trick. That's the trick here. It's quite unusual to see, but it's visible. It's a simple trick. Now why I'm using that, now why I've used this trick is, you'll see You'll just see in a minute why I use this. C square, 2c squared was right. Yeah, 2c squared minus v by c, 0, 0. And this is v by c minus v square by 2c square, 0, 0. And again it was 0, 0, 0, 0. Since we split it out, these two terms are 0 as well. Now this particular matrix is G mu nu. We know this. This is the diagonal metric. But this, we name this metric as mu nu, omega mu nu. Now this metric omega mu nu in this equation, did I name this equation? No, right? So let's name this as 1.47. Yeah. So this, the metric omega mu nu in this equation is anti-symmetric. What do I mean by anti-symmetric is under the exchange of any two indices downstairs, it reproduces the metric, but that comes with a minus sign. This is anti-symmetric. Can be seen by taking the transpose. You can see this. If you want to see this, just take this transpose of this matrix and we'll see this property. So thus we know it satisfies all the condition that has been asked in this question. So it satisfies this particular condition. It satisfies this particular condition as well. In the question, thus we have solved the problem. So yeah, so if you want, you can just satisfy yourself by writing this. Doesn't mean anything, but yeah, just nah, you don't have to name this equation. It's fine. We are not going to use it. So that was the two problems on the STR, and we solved them both. Great, great. That's fantastic, fantastic. Now we'll go back to this. I I particularly want to emphasize a very important topic, which is the scalar product. Let me write it down. Scalar product of two vectors and the scalar function or scalar functions. Fine. So, what is scalar? What is scalar quantity? Any object that remains. So, in the context of STR, what I mean is any object that remains invariant, like x mu upstairs, x mu downstairs, is a scalar quantity. Now the scalar product of two vectors. Now let's take two vectors, a mu and b nu. So the scalar product of these two vectors will be written as a mu b nu, g mu nu, a mu b nu, or a mu downstairs and b mu upstairs. So this is the scalar product. This is the way that is written. So if you want to write it down explicitly, we can do it. We can say a0 b0 minus a vector dot b vector is a0. We will use this a0 b0 plus ai bi. That's that simple as that. This is equation 1.48. This is, yeah. So this is the way that the scalar product of any two vectors is written down. So So this is going to be very important to us when we are going to dive into the quantization of scalar fields, real scalar fields, complex scalar fields, and so on, Dirac fields. This particular thing is going to be very, very useful for us. Now, if yeah, so if I have, say, if phi of x is a scalar function, is some scalar function where psi is a scalar field. Let's say it's a scalar field. We can calculate a small change. Can calculate a small change in this or in it if you prefer. Uh, we will denote this by delta x. So what we can do is I have a scalar field. Let me explain it. I have phi of x as the scalar function where psi is some scalar field. I want to calculate a small change in it, a very minute change in the scalar field. I denote this notation. I use this notation and we can calculate this by this particular equation x mu delta x mu. This is equation 1.49. Let me box it and let me explain what each term means. Now, this particular quantity, okay. This is scalar, okay. This is scalar, right? If the left hand side is a scalar quantity, that means the right hand side should also be a scalar quantity. This we know is a contravariant vector. It's a contravariant 4 vector. It's a contravariant vector. So what this means is this must be a covariant vector, right? If you don't understand, just look at this particular definition. This is a contravariant, this is a covariant, contravariant, covariant. So they produce a scalar quantity. Likewise, if this is a contravariant, this is a scalar, we know this is a contravariant vector. This must be a covariant vector in order for this to be equal. So this must be a covariant vector. This must be a covariant vector. So what we can do is we'll use a shorthand. The shorthand is very important. It's going to be very useful for us. Dou mu is dou by dou x mu. This is the covariant vector. And we can write similarly upstairs, which is contravariant, which will look like this is contravariant. Okay, when it is in denominator, the rules are different. I mean, it's not, when I say different, I didn't mean in a very analogically mathematical way. Uh, you see this is up, so you must think like, oh, this must be a contravariant vector. No, it's in the downstairs, it's in the denominator. So in denominator, when it is up, when it goes up, when this index goes up, this becomes downside. That's why it's a covariant. It's low, it's a covariant. And similarly this one. So we don't confuse it. The thing is, this requires a lot of practice. It requires a lot of handling of the notations, such as this Greek indices, Latin indices. So I think the most genuine book would be an introductory book on GR. But however, this is not a course on GR, but rather we are studying the special theory of relativity in a very mathematically structured way. And I studied it in this manner, and because my professor taught me, and I didn't go out and look for some notes where they use this particular, but you can go and literally look for something like this. So now what we can do is we can go ahead and define x mu. Oh, my handwriting. X mu to be dou by dou x to be 1 by c d dou by dou t vector, and this is straight from the definition book. Okay, this is nothing to do with what I'm. This is nothing. This is nothing that I'm creating or deriving. This is just straight from the definition book. We are just we did it in 1D, now we are doing it in 3D. That's all the differences. This equation 1.51. So for some arbitrary vector, let's take no okay yeah let's take some arbitrary vector. Let's take a mu for example. It's an arbitrary vector. So what I can do is I can operate this dou mu a mu on this 4 vector. What I get is 1 by c dou by dou t a0 del vector a vector. So this is equation 1.5352. So okay, I can write this as a mu. Let me explain why. Since negative into negative, you see negative into negative is positive, and we use this particular equation equality, this particular equality, negative negative is positive, so this particular sign goes away, and this particular equality gives us a rule to write this. This is very important. I'm going to mark this as equation 5.3. So whenever you come across this particular term, we can really exchange this upper indices, lower indices, upper indices, lower indices. It doesn't matter. It doesn't matter. It really doesn't matter. What it matters is this particular thing operates on this 4 vector, and we get so. mm, should I introduce this? Yeah, yeah. We can go ahead and further define what's called as a box operator. This is a wave operator, is a more appropriate word, wave operator, and this is a scalar operator. So this is a scalar operator, and the notation that goes is 1 by c square dou t square minus del square is dou mu downstairs, dou mu upstairs. Now you know why it's a scalar operator, because this is contracted and you get a scalar operator. These are operators, right? They are individually operator, and the indices are contracted and they give you a scalar quantity. Thus, they are called as the scalar operator. This is a very important operator that we will definitely use it in the ongoing QFT course. This is equation 1.4. This is very important. Now, in order for you to get familiar with this notation, what I'll do is I'll just give you an example of the very known example from STR, which is the momentum 4 vector. So we define the momentum 4 vector in the STR is E by C P vector, which is equation 1.55. So what I do is I took an arbitrary particle which has the momentum 4 vector, which is given by this equation. So E is the energy of the particle. What we can do is we can go ahead and define the invariant scalar product. We can define the invariant scalar product. You know by now this is this, right? So let us calculate P mu, which is E square by C square minus square, which is M square C square. We see that now, okay, yeah, we see that it is coming out merely as a number. M is a number, C is a number, M is some arbitrary number of the mass of the particle. C is definitely a number because it's the speed of light. It's coming out as a number. What is so this merely validates what I said here, which is a scalar quantity. It defines a scalar quantity. This is nothing but the famous mass energy relation. You might know this from your STR course. I'll just name this equation as 1.56. We're not going to use it anyway, but just so what we can do is we can go ahead and we'll okay before finishing this video we can just go ahead and do a sanity check on our understanding. A simple exercise, nothing big, nothing bad. We can do this. We have, let's say, if x mu is upstairs is ct x vector, our task will be to calculate the dou mu x mu. Oh my god, my handwriting. X mu. This is our task. Simple three line calculation. Simple three line. Okay, let's do this. I'm writing it in a very full-fledged notation. This was a shorthand notation which was used here. Dou mu is dou x mu, dou x mu. So this gives dou x zero plus dou x1, dou x1 plus dou x2, dou x2 plus dou x3, dou x3. So this is 1 plus 1. Oh my, plus 1 plus 1. This is 1. This is same numerator denominator, same numerator denominator, same numerator, same. This is 1 plus 1 plus 1 plus 1, which is 4. So what we get is again a scalar quantity, a mere number, which is dou x mu is equal to dou mu x mu, scalar quantity, which is 4. This is just the sanity check that we did, and we just named this equation 1.57. Now that's all for this video. Now this lecture, these notations are going to be very useful when we go on further studying the quantization of fields. So that's why I wanted to introduce it here only, because I don't want to drag it along, because I don't want to break the rhythm when we'll do that. So in the next lecture, we'll definitely look into what's called as the natural unit, that going to be the base, that going to be the base of QFT, because it's very important for us to know the natural units. The conversion factor between the natural units and the normal units is going to be very important for us, and we'll definitely have a different session on it. So thank you so much for watching. If you have any doubt, just contact me personally. My email is in the description, or if you want to ask in the comment section, that's also is fine. You can go to the website, you can go to the course website and find many other articles as well. So thank you so much.